Hello, everybody. I'm sorry this has to be a video lecture. As I mentioned in class, my wife has surgery and something happened with regard to the timing of the surgery. So I am unable to make it to class or even hold a Zoom lecture. Okay, in the last class, because of Amazon Web Services issues, many of you were unable to complete the homework on non-homogeneous second order differential equations with constant coefficients. So I took a small portion of the subsequent lecture, which is forced vibrations, and forced vibrations are a non-homogeneous equation. And we went through that slowly to make sure you understood how to do it. Anyway, the complete slide pack of the last lecture has been uploaded. Now, I will do the second half of forced vibrations in this lecture, albeit through a recorded lecture. So I call this lecture 15 part 2. We'll look at two examples in this class. First, I want you to recollect in the last class, we had an experiment done in class where two of you guys made a whistle with a bottle, and the two bottles were close to each other but not exactly the same. One had a slightly higher frequency than the other. So when the two students made noise with their whistle with their bottles and they were standing side by side, the whole class was able to hear what are known as beats, something of that nature. And so today we will first try to understand beats, and then we will try to understand RLC circuits. Okay, next slide. So, coming back to a mass spring system, notice there's no damper here. In the last class, we studied the case with a damper. We're doing it without a damper now, again, as an exercise, just to go through the process again, so you guys get familiar with solving non-homogeneous equations. Up on the title is, let me try to get a pointer, there we go. Up on the title, is the differential equation we're solving, y double prime plus k over my equals f0 over m cosine omega t. Now, there is no damping, so there's no c over m. So it's a mass spring situation. And part A, if I have it in red here, is the complementary solution or the homogeneous solution. What do? We set the right-hand side to 0 and say y double prime plus k over my equals 0. This is a homogeneous solution. And instead of solving it, I say, let's take the mass spring damper solution in its entirety and simply set the damping coefficient to 0. So this is the mass spring damper solution for the homogeneous equation, where e to the minus c over 2mt, this is the exponentially decaying term, multiplied by c3 cosine omega t plus I c4 sine omega t. 2 points to make. This omega is square root of 4k over m minus c over m squared, whole divided by 2. Just bear with me for a second. And another point to make is IC4, the combination of IC4 will be a real number, and you know how to do it when you apply initial conditions. So therefore, we have, this can be rewritten as, when the damping coefficient is 0, because we are interested in no damping, so simply set c equals 0. Exponential of minus c over 2mt is exponential of 0, that will be 1. And over here, when you say c over m is 0, because there's no damping, with square root of 4k over m, there's 2 square root of k over m, the 2 and 2 cancel, and you get square root of k over m, t. Plus IC4 sine square root of k over m t, which is again c3 cosine omega naught t plus IC4 sine omega naught t. Notice here, by setting the damping coefficient equal to 0, you got the solution for a mass spring solution, and here omega naught is square root of k over m. Next. So, square root of k over m is omega naught, angular velocity in radians per second. The homogeneous equation, as discussed in the class, represents free vibrations in response to initial conditions. No forcing, because the right-hand side has been set to 0. Now, and the end result would be that the mass spring, the displacement of the mass will go up and down forever. It will never diminish. There's no damping. Now, for the particular solution where the right-hand side is not equal to 0, there may be 5,000 different particular solutions. Any one is enough for us. So the way we find our particular solution is, we cannot set the right-hand side to 0 now because we're finding the particular solution. But we look at the right-hand side and say it has the form cosine omega t. So we go to our trusty table. On the right-hand side, if you have k cosine omega t or sine omega t, then try a particular solution of a cosine omega x plus b sine omega x or omega t. Okay. So we're going to try a particular solution of a cosine omega t plus b sine omega t. Then therefore you can take the derivatives. You know how to do that. Yp prime, the first derivative, cosine will become sine with a minus sign and omega multiplier. First derivative here, sine will become cosine without a minus sign, same positive sign and a multiplier omega. And y double prime will be minus a omega squared cosine omega t minus b omega squared sine omega t. Essentially say is minus omega squared y. You see that? Minus omega squared y equals y double prime. Anyway, so y double prime, particular solution, plus k over m yp, the particular solution, must equal the right-hand side. Right-hand side is f0 over m cosine omega t. But we have a formula for yp double prime, which is this. So let's put it in there. Minus a omega squared cosine omega t minus b omega squared sine omega t plus k over m yp. Yp is right there. A cosine omega t plus b sine omega t. Collect the cosine omega t terms. You'll have minus a omega squared plus a k over m. Collect the sine omega t terms. You'll have minus b omega squared plus bk over m. K over mb. So the left-hand side, which now represents this, should equal the right-hand side if yp is a solution to the differential equation. If that is so, then the coefficient of cosine omega t has to be 0. And I apologize. The coefficient of cosine omega t should equal f0 over m, and the coefficient of sine omega t must be 0. So let's do that. Set the coefficient of sine omega t to 0, which means for any omega, any driving force, omega is the frequency of the driving force. So omega can be anything, and this combination can be 0 only if b is 0. So b is 0. The second thing is this coefficient of cosine omega t, which is minus a omega squared plus k over m a, which I have right here, should equal f0 over m. F0 over m. Coefficient of cosine should equal the coefficient of cosine. Coefficient of sine should equal 0 because there is no sign there. So this gives you a value for a, f0 by m, omega naught squared minus omega squared. So yp now is a cosine omega t, you have a here, a cosine omega t, plus b sine omega t, b is 0, so this is our complete yp. I'm going to try to emphasize again. What is omega 0? It is square root of k over m. What is omega? It is the frequency of the forcing function. They're different. You can push and pull the mass at a different frequency, which is omega, but the natural frequency is omega 0, square root of k over m. Now, here we are. We've done the homogeneous solution, which is by setting the right-hand side equals 0, and we've found a particular solution using a table, using the method of undetermined coefficients. So when you combine the two, the general solution to our non-homogeneous equation, the general solution is the homogeneous solution plus one particular solution, any particular solution. And we found one. That is the homogeneous solution plus the particular solution that we found in the last two slides. And now if this is so, you can take the derivative. Y prime, why do we need the derivative? Because of initial conditions. We'll explain that to you in a second. Y prime is yh prime plus yp prime, and you can take the derivative of each of these terms. You know how to do it. Why do we need to do that? Because the initial condition is on y of 0 and y prime of 0. Now, what we're doing next is, I'm going to take an example. We're going to take an example. Say C is 0, because we are considering the case of no damping. And if it's about homework, it's delayed to next week, to next class. Something else? Okay, C is set to 0. I've taken a value of K and M like we have done before. I'm sorry, someone came into the room, so I was explaining to her what I was about homework. So let me come back to this. But you see here, the initial condition is y of 0 equals 0, y prime 0 equals 3. That's the reason why once we got y, we got its derivative also. Square root of k over m is omega naught, and k over m is omega naught squared. Y of 0 equals 0 implies, well, let's try it. Y of 0 equals 0. When time t equals 0, cosine is 1, sine is 0, cosine is 1. So C3 plus this constant must equal 0. Therefore, C3 turns out to be this constant. And here, omega naught squared, we had evaluated in this example to be 26.5. Next, so now we can rewrite y, because we already know C3. So y is now C3 times cosine omega naught t, omega naught is 5.15, plus I sine omega naught t, IC4 sine omega, we don't know IC4 yet, plus F0 by m is 1, omega naught squared minus omega squared cosine omega t. Now, y prime 0 is 3, which is the reason why we did this derivative here. So we come in here and you say, at time t equals 0, well, sine is 0, cosine is 1. So IC4 omega naught equals 3. IC4 times omega naught is 5.15 equals 3. So IC4 equals 3 over 5.15. Or you can write C4 has this imaginary number, and when you multiply it out, the IC4 will become a real number, because I squared is minus 1. So y is F0 by 26.5 minus omega squared cosine. Where did we get this from? Right there. We already found this out. And then we just found out C4 and IC4, that is this. And this is the F0 cosine omega t divided by omega naught squared minus omega squared, the particular solution. So that is C cosine 5.15 t minus delta, you see, sine omega t, cosine omega t, plus d cosine omega t. These two can be combined, as we talked in the last class, into an amplitude and a phase. This coefficient and this coefficient, or this a1 and a2, can be combined to give you an amplitude square root of a1 squared plus a2 squared, and a phase delta, which is tan inverse of a2 over a1. And d cosine omega t is exactly that term. So let's examine what we get when we try various values of omega. For example, here's a forcing function that is a cosine. This is f cosine omega t. And in this example, the forcing function goes from plus 1 to minus 1, so f is 1. And then, here's what we get for the displacement if Omega naught is 5.15 as we calculated in the previous slide, and the forcing function is 7 radians per second. F0 is 12.5. This is a pretty jagged shape. So if you look at the mass, it'll be jerking around. Look at this example. Here what we did, we increased, F0 is held constant at 12.5. We increased omega to 6 now, decreased omega to 6. So we brought it closer to 5.15. When you bring it closer, look, it kind of looks funny. Looks like there's something that's almost sinusoidal, there's large amplitude, and it breaks down and then becomes sinusoidal again. Let's examine this some more. Next. Next we have F0 of 12.5, same as before. Omega now is smaller than omega 0. Here it is larger, there's larger, here it is smaller. And again it looks kind of like the case where omega was 6. And not at all like the case when omega was 7. Now look at a case where we bring omega closer to omega 0, 5 and 5.15. You had 6 and 5.15, you had 4 and 5.15, now it's 5 and 1, very close. It looks like you have some large amplitudes here, becoming very small amplitudes, and then becoming large amplitudes again. So what I did was took this last signal where omega is 5, very close to 5.5, and showed you a long duration. How does it look? You have large amplitude vibrations, almost 0, large amplitude vibrations, almost 0. You see this? Now, in the last class, when the two gentlemen blew into their respective bottles, which are slightly different frequencies, you see this? Omega of 5 and omega 0, 5.15, slightly different frequencies. You could hear in class, wow, 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 wow. So the frequency omega and omega 0 are very high, but the wow, 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 that is this frequency. Wow, 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 wow. Okay. So these are called beats. So, for the mass spring damper system, forced vibrations, we found a particular solution, and this is an iClicker. Unfortunately, this class is not live, so we cannot do iClicker, but what I'm trying to say is, we found a particular solution. We found A is so much and B is so much. This is a particular solution. Now, minus omega squared, let me go through it again. This is Yp, a guessed form, a form that we've selected. This is Yp prime, Yp double prime. We plugged Yp double prime and Yp into the left-hand side of the differential equation, collected all the sine and cosine terms, and said it has to equal the right-hand side of the original differential equation. And then we said the cosine term coefficient should equal f0 over m, and the sine term coefficient should equal 0. So the sine term coefficient should equal 0. What does this imply? Does this imply b equals 0? Does it imply minus omega squared plus k over m equals 0? Either A or B. The answer is it has to imply b equals 0 because omega can be anything. You can vibrate, your force can oscillate at any frequency. Okay, next. Now, coming back to RLC circuits, resistance, capacitance, and inductance. Here, at any instant, the current is the same. The current that goes through here equals the current that goes through here, equals the current that goes through here, and so on. The current is the same throughout the circuit. And this is a combination of everything you learned before. And then the voltage drop across the inductance plus the voltage drop across the capacitance plus the voltage drop across the resistance equals the voltage rise across the battery. And here we have an alternating current. The battery gives you fluctuating current, like the outlet in your wall. AC supply voltage is E sub E of time, okay. The resistance at any time, the voltage drop across the resistance is simply IR, current times resistance, which is Ohm's law. But as we've discussed many times before, the current I is the derivative of charge in the capacitor. The rate of change of charge in the capacitor equals the current that's flowing into it. And the example I gave in class was to say the rate of change of the volume of water in a bucket equals the rate of flow of water through the hose that is feeding the bucket. Inductance. The voltage drop across the inductance is L, which is measured in Henry, times the rate of change of current, di over dt. But I is dq over dt. So voltage drop across the inductance is L d squared q over dt squared. You see, instead of di we put dq dt. So d by dt of dq dt is d squared q over dt squared. And one more relationship. So you're aware, capacitance charge is integral over time, from time 0 to this current time, of the current that's flown into it. The total amount of water in the bucket is the integral, sum total of all the flow that has come through the hose to fill the bucket. For a capacitor, the voltage drop across the capacitor is its charge divided by its capacitance. The capacitance is measured in farads, and the charge is integral I dt. L, and the equation now to say the sum of all the voltage drops equals the total voltage drops rise across the source. L d squared q by dt squared, that is the voltage drop across the inductance, plus R dq dt, that's the voltage drop across the resistance, plus q over c equals Et. Q over c is the voltage across the capacitance. This is a second order differential equation. So, or you can write it as an integral differential equation where you have L di in terms of current. But for now, let us work with the charge. Second order equation, d squared q over dt squared, dq over dt, q over c equals the right hand side. This has constant coefficients and is non-homogeneous. Now, look at this problem. Find the current IC in RLC circuit with R equals 11 ohms, L equals 0.1 henries, and capacitance is 10 microfarads, 10 to the minus 2 farads. They're connected to the source EMF, 110 sine 60 times 2 pi t, that's 110 sine 377 t. See, this is 110 volts, E is 110 volts, sine, it's a sinusoidal variation. It goes from, sine goes from plus 1 to minus 1. So it goes from plus 110 to minus 110. And what is this 60? That's 60 hertz, 60 times a second. For each time that it goes through, angle of 2 pi, one rotation is 2 pi. So 60 times 2 pi is that many radians per second, that is omega. Omega is 377. So the voltage E sine omega t is L d squared q by dt squared plus R dq dt plus q over c. This is the equation based on physics of the circuit from the previous slide. So you can put in the voltage, 110, that's the sinusoidal variation. Put the value of L, R, and capacitance. Capacitance in the denominator. The homogeneous solution, and what I've done is divided through by 0.1. Okay, so 11 becomes 110. 1 over 0.01 divided by 0.1 becomes 1000. The homogeneous solution, right hand side is set to 0. And the solution is you find y equals e to q equals e to the lambda t, and write the characteristic equation lambda squared. Find lambda. Lambda is minus 10 and minus 100. So the solution Q is A e to the lambda 1t plus B d e to the lambda 2t, not dE. e to the lambda 2t. Now for the particular solution, let us assume, because the forcing function has sine 377t, let's assume the particular solution has the form c times sine 377t plus d times cosine 377t, just like we did in the previous two examples. Then in small font I've written here qp prime, qp double prime, the derivatives. And then we write the differential equation. This is 0.1 times qp double prime plus 11 times qp prime plus 100 times qp equals the right hand side. And I won't bother with the details, but we're able to find a general solution, which is q is qh. I'm sorry, this is e to the minus 10t, and this is e to the minus 100t. I'll fix that before I finish the lecture, but I don't have time to finish it before this recording. Then, and this is the particular solution that we got. We had c sine 377t plus d cosine c 377t. Through this process, we found c was as minus 0.00717 and d was minus 0.00211. So now we have the general solution. We still don't know these constants for the homogeneous solution. We usually call them C1, C2, but it's okay, I call them A and B here. So this is the form for the general solution. At initial time, the charge is 0 and the current is also 0. At initial time, charge is 0. Before we go any further, the current itself is the derivative of Q, and you know how to take the derivative of each of these terms. And this is what you'll get when you take the derivative. Q of 0 equals 0, charge is 0, time t equals 0, means, let's come to Q. That goes to 1, that goes to 1, that goes to 0, that goes to 1. So it's A plus B minus 0.0021 equals 0. Then I of the current at time t equals 0 says the second line here. When time equals 0, that goes to 1, that goes to 1, that goes to 1, and that goes to 0. You have minus 10a minus 100b minus 2.7 equals 0. You have two equations, two unknowns. You can solve for them. You get a and b. So the current now is given to you as minus 10 times a, so you and e to the minus 10t, so you get that. You know a now. Minus 100b, you know b now, so you can get that term, and that term. So this is a complete solution for the current. Why are we showing the current? We wrote the differential equation in terms of charge, but the problem asks you to find the current. And that's why we took the derivative of charge and we found the current. Okay, I apologize for making this a video lesson, but it does look, it's just a personal clash related to my wife's health. So thank you for your consideration.